Hello, my name is Kelsey Wimberly, and I'm going to be showing what I did in my AI class at DigiPen. The first project was using behavior trees to create unique AI functionality for at least 4 characters, so I chose to make a simplified version of Five Nights at Freddy's. As you can see, my 4 agents are the animatronics featured in the game, which all follow their own movement patterns to reach the player. I programmed all of their paths to be similar to the original game, but I modified Freddy and Chica so that they would not enter the same space for this project. I also added player control for the doors, as well as win and lose conditions, and I made the timer go much quicker than in the actual game. Here is what losing looks like. And here's what winning looks like. I enjoyed working with behavior trees in this project, as I was provided a behavior tree creation program, and I just needed to create the code for the individual nodes. And I liked the freedom to choose how to implement this project. The second project was A-star pathfinding. This is done with a combination of Dijkstra's algorithm and greedy best first algorithm. The algorithm uses a closed list and an open list, and it starts with the player's location, which is placed on the closed list, then adds all of its neighbors onto the open list. After that, the algorithm searches the open list for the cheapest node, which is found using the distance from its neighbor, which we track by calling it the parent node, and the distance to the goal using one of the few heuristic cost options, which I can switch between here, though Octile is usually the most optimal. For debugging purposes, we can step through the algorithm one node at a time, and we can color the nodes on the open list blue and the nodes on the closed list yellow. I also implemented rubber banding, which checks if a node can be removed for more concise movement, and smoothing, which makes turning look a bit more natural. The combination of these two makes movement look incredibly realistic. The third project was terrain analysis. There are various layers that needed to be created for the hide-and-seek functionality, starting with openness. Openness shows how close a space is to a wall tile, or the edge of the map. The next layer is visibility, which shows how much space is seen by other open tiles. Visible to agent indicates which tiles can see the player agent, with light green tiles being one step away from seeing them. So, if you were using this for a third-person shooter, for example, the light green tiles indicate good spots to hide after taking a shot at an enemy. The search layer shows what the player can see, and the tiles progressively get lighter as the player no longer looks at them. This is good for tracking areas you have recently looked at. Propagation is like dropping a bit of paint in a spot and watching it spread out. The same can be said of normalized propagation, though this maintains the strong color throughout. As a note, dual propagation was not required for this project. All of these layers are used in the hide-and-seek functionality. The enemy will start coming for the player, and the green tiles show what they can currently see. The propagation and search layers come in when the enemy does not see the player and needs to begin searching, and they will prioritize the deeper red areas as they indicate that the enemy has not searched there. It was very interesting to use all the layers together for hide and seek, and watching the enemy hunt for the player is very cool. The final project was a group research project. My team chose to create a sparse voxel octree for pathfinding in a three-dimensional space. An SVO is particularly useful for this because it breaks down sections that contain obstacles into even smaller sections, while leaving large, open sections at their biggest size. We built this project in Unity, and we created editor tools to generate and visualize the SVO. Here, it checks for objects with the obstacle tag inside the SVO upon generation, which allows the cell sizes to be broken down into their correct layers. We can see each layer in detail here, being able to go deeper until the lowest layer is the size of each obstacle. We then modified the pathfinding algorithm from Project 2 to work with the third dimension, as well as being able to traverse between layers. Moving through the same or higher levels is easy, but moving into a deeper layer requires checking which cells are actually direct neighbors of our current path node. Overall, sparse voxel octrees are a great way to do pathfinding in 3D with lots of obstacles. These were my AI projects created at DigiPen. Thank you for watching.